Hello everyone and welcome back. So today we are going over yet another example. So without further ado, let's just get right into it. All right. So how do we solve this problem? First, we wanna just solve for the reactions. All right. Sum of forces in the y direction equal to 0, and then we have two forces. We have two reactions, sorry, AY and BY, right? AX equals 0 because there's no horizontal forces. So we have AY plus BY minus 3 times 6, so that's 18, right? Equals 0. So we have AY plus BY equals 18, all right? And then we can do a sum of moments about point A counterclockwise equals positive and set that equal to 0, all right? So we can take this distributed load, replace it with an equivalent point load, and this distance would be half of the total distance, okay? Total distance is 6, so we're going to take half of that, which should give us 3, right? And the equivalent load is 18 kilonewtons because that's 8 times 6. Oh, 6 times 3. Whoa, 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 whoa. So we have 18 times 3, right? That's from the distributed load, and it's rotating it clockwise, so it's negative. And then plus 4by equals 0, and then 4by equals 18 times 3, which should be 54. And then by equals 27 over 2, 13.5. So AY would just be 18 minus BY, which is 4.5. All right. Now, these are the two numbers we're going to get for our reactions. So let's just write those in. 4.5 and BY equals 13.5. All right. So I'm assuming you guys know how to solve reactions already, but if you don't, please refer back to the previous videos. I'd like to think that they're helpful, and I go in more detail. All right, let me just erase this. Okay, so once we have that, we can start solving for the shear force and bending moment diagram. All right, shear force diagram, very simple. Again, trace the diagram. All right, trace the diagram. So if we see AY at the beginning, at the very start, acting 4.5 upwards, we just go 4.5 up, okay? And then from here to BY, right, there's 4 meters, and then with a total of 3 kilonewtons per meter, right? So that's a total of 12 kilonewtons, right? And then that's going downwards, okay? So 4.5, so if it goes down from, let me draw a line here. If it goes down by 12, right, that just means it's 4.5 minus 12 in total, and then that's equal to it's negative 7.5. All right, so how we got this number is just simply starting at the very left, we have AY equals 4.5, and then from 0 to 4, we have 3 kilonewtons pushing down, right? So from 4.5 all the way minus 12, negative 7.5. Okay, so once we have this, we find that BY equals 13.5, so we can add 13.5 to this negative 7.5, shoot back up to 6, right? And then finally, the last segment from BY to the end, so from 4 to 6, we have 3 times 2 is the total distributed load, so we just go back to 0, right? When loads go up, we go up. When loads go down, we go down. And because it's distributed load, it's a straight line through, okay? So here comes the more tricky part, right? How do we find the bending moment diagram, all right? So this one is a bit more tricky because we need to find what these distances are, okay? So because the simplest way to do it would be to find these two areas here. Okay? So again, how do we do that? Well, we can use similar triangles, right? So imagine we're trying to find this slope, all right, between this 4.5 and the 7.5. If we draw a triangle like this, right, to find this slope, right, this portion, the height of it, right, if let's say I use a blue highlighter, right, this slope, okay, that's 4.5 plus 7.5, right? Because it's this total distance here. Okay, keep that in mind. This distance here. Okay, so, and then this would equal to 4, right? And then the smaller triangle, let me use a different color here. The smaller triangle within this big triangle would have the same slope, right? So the smaller triangle would have a height of what? 4.5, right? And a distance of x1. We don't know x1, but we're trying to find that. Okay, so we can set up our similar triangles, right? 4.5 plus 7.5, 4.5 plus 7.5 equals 12, all right? So we can just simply set it up as 4 over 12 equals x1 over 4.5. Okay, does that make sense? It's because it's this over this should give you this over this, right? You can do it the other way around. You can do this over this. It doesn't matter. Or even you can use this triangle. But the key thing to remember is the other triangle comes from here. Or maybe you can use this one and this one, right? But similar triangles all apply, okay? So once we have 4 divided by 12 times 4.5, right, we find that x1, which is this length here, equals to 1.5 meters. Okay, so once we have that, you can simply write that down here, and x2, we'll call that x2, 4 minus 1.5, that equals 2.5 meters. All right, and this is just 2 meters. Okay, so with that in mind, it's actually quite simple to solve. So we're going to find this area, we're going to find this area, we're going to find this area, all right? So A1, we'll call that area 1, right? That's 4.5 times 1.5 times a half, okay? And that's 4.5 times 1.5 times 0.5, I guess, okay. So this equals 3.375, whatever that means, okay? You don't have to keep too many decimals, but I'll just keep exact numbers just because, okay? So next we have negative 7.5 times 2.5 times 0.5, right? And we get negative 9.375, okay? And then finally for this area, 6 times 2, 12 divided by 2, that's 6, okay? So how do we solve this? Okay, we go from 0 at the start, right? Because there's no moment. If we look back to this is a hinge support, so there is no moment applied, resisted at this point, right? Therefore, moment is equal to 0, and we're gonna go from here to here. We are going to go up a total of 3.375, okay? So if you're curious on how I drew this line over here, remember more area equals more of whatever you're adding and subtracting, right? So at the start there's more area, so it's a steeper slope, and at the end there's less area and you get a more gentle slope, right? And then finally we have minus this area, right, the second half, right? So we're going to go from 3.375 and then subtract 9.375, and that should equals -6. All right, so it's just this number minus this area over here. Okay, so we're going to go down, and we have less area at the beginning, so we're subtracting gently. And then as we get to the end, we're subtracting more and more till we get something like this. And finally, the last area, we add 6 to this, so more area, more increase, less area, less increase, and boom, end up at 0. Okay, so that has been this problem. A trickier problem, actually, because there's a lot of things that need to come together in order to solve this problem, but I hope you understand that all of these problems really have the same steps, right? You first find your reactions, right? Find your reactions, right? Second, draw a shear force diagram. This shouldn't be too hard, but if this was a triangular load, it would be a bit harder because you would have curved lines here, but since it's uniform in this example, we don't have to worry too much, okay? And then second, we have to find the areas under the shear force diagram in order to find the values for the bending moment diagram, okay? And how we do that? We can use similar triangles, all right? Remember, this is a triangle. You can use this as a triangle, whatever works, okay? And that's how you get a distance that's split up like this. And once you have those, calculate your area. Again, you know, more area at the start, more increase, more area on this side, more increase here, right? Vice versa. Okay, so that's it for this example. I'm looking forward to seeing you guys on the next one, all right? So I hope you learned something new, and it seems like a few of you are stumbling across my videos, so that's always good. I don't know if you're staying at the end towards this monologue of mine, but if you're here, welcome, and thank you for sticking around, all right? I'll catch you in the next one.